Briefly, I just wanted to go over the agenda for what we're going to be covering today. We're going to start with just derivatives, going over all the derivative rules. We're then going to segue into partial derivatives and multivariable calculus, and then understand how partial derivatives are used to calculate gradients, and gradients are very important for machine learning algorithms. Then we're going to move on to the linear algebra side of things. We're going to look at Cartesian vectors, and then we're going to dive into distance metrics, which are also used a lot in embedding spaces. We're going to cover the 2 norm or magnitude, as well as cosine similarity. And then we're going to finish it off with a little bit more of an advanced topic, such as eigenvalues and how they relate to principal component analysis. So I hope everyone's excited.
Looks awesome. Okay, we're good to go. Take 2. Thanks for your patience, everyone.
Thank you so much. Okay, so yeah, we're diving into derivatives. So the 4 main rules we're going to cover today are power rule, product rule, quotient rule, and chain rule. But before we get into derivative rules, we have to understand first what is a derivative. So many of us learn derivatives also as the instantaneous rate of change. So essentially, you have to think of this conceptually. If we have 2 points that are really close to each other, what is the rate of change from going from one point to a next point? So if these points are far away from each other, we have what's called a secant line that connects them. However, what I want you to imagine is I want you to imagine these points getting closer and closer together. And then essentially what's going to happen is these points are going to be essentially on the same spot, so that we end up taking a tangent line to the curve instead of a secant. So that's the fundamental principle of derivatives, is that you have this instantaneous rate of change. And essentially what that is, it's the slope of the tangent line to a curve. And this has so many applications, more that like across like finance, biology, physics, machine learning, engineering. And it's a really great, just fundamental mathematical concept to understand. So that's kind of the why and what behind derivatives. So now that we have that, we're going to go into each one of these rules. Okay, so let's change up the colors. So first of all, we're going to start with function notation. So I hope everyone's familiar with this. So we have f of x. So essentially what this is, it means that we have some function, f, which is our independent variable, and it changes with respect to x. So x is our independent variable, and f is our dependent variable. So essentially, you can think of it as a machine. So we're feeding in different values of x into our f function, and then it's going to spit out the result for us. So for example, if we have x plus 2, we'll feed in all different values of x, and then we will get our result. So if x equals to 1, for example, then we have 1 plus 2, and then the result of our function would be 3. So that's just a little bit background on functions, just to make sure everyone's comfortable with function notation. So for our beginning, we're going to start with power rule right over here. So power rule tells us that if we have some function f of x, and it equals to, let's say, x to the power of n. So power rule has to do with when we have an exponent. So in this case, n can be any integer. So here we have, in terms of mathematical notation, we can write n is an element of the integers, which essentially means n can be any whole number, positive or negative. So when we have something set up like this, the power rule tells us that the first derivative of f with respect to x equals to n times x to the n minus 1. So essentially what's going on is you're taking your exponent, putting it as your coefficient, and then in your exponent here, you just have to subtract 1. And in terms of notation, this here is called prime notation for a derivative, but it can also be written with Leibniz notation, such that you'd have dy over dx. So again, this is the derivative of y with respect to x. So now that we have this notation, we're going to go through an example to make sure that we can see this in action. So for example, today we're going to consider a function that's f of x equals to x to the power of 3. So following our power rule here, we're going to use this rule. So our f prime of x equals to n, so 3x and then n minus 1, so 3 minus 1. So then we get 3x to the power of 2. And this rule you'll end up using all the time in conjunction with the rest of our rules, so make sure you have this one written down. Okay, so next off, we're going to move on to the product rule. So the product rule, just like kind of how its name says, that's when you have a multiplication between two different terms. So say, for example, our f of x, our function, is now composed of two functions. We have, let's say, g of x multiplied by h of x. So we have our function is now equals the multiplication of two functions. So because of this, we have what's known as a product. So I'm going to show you now the general rule that how we can find a derivative when we have this situation. So you would say f prime of x equals to the derivative of the first. So we're going to call that g prime times the second, so h of x, and then plus the derivative of the second. So that'd be h prime multiplied by the first. So we just have g of x. So this is the general formula or format for product rule. So we'll show an example of that in action. So say, for example, we have f of x equals to x plus 2 multiplied by x squared minus 7x. So how I like to break this down is, first of all, I recommend everyone to label your functions. So we'll call this part g, and we'll call this second part over here h. So now we're going to go ahead and take the derivative of g and then h respectively, and then we're going to put it together using the formula. So g prime, the derivative of the first, we can use power rule. So we have the derivative of x, which is just 1. And just so you know, the derivative of any constant equals to 0. So this 2 is going to go away. And then if we look at the derivative of h over here, we can use our power rule, which we just learned. So we will end up with 2x and then minus 7. And now we can use both of this information, and we can use that to find the full derivative. So following our formula over here, we have that f prime equals to g prime. So we've got 1 times h, and h is x squared minus 7x, and then plus h prime. So we've got 2x minus 7, and then multiplied by g, which is x plus 2. And that is the derivative using product rule. So we could go ahead expand and simplify this, but for the sake of time today, I'll leave that as an exercise. I mostly just wanted to show how this rule works in action. Okay, so now that we've got product rule, we're going to go on to quotient rule. So as you can imagine, if product was the multiplication between two terms, quotient rule is going to be the division. So we use quotient rule when our function is set up as, let's say, g of x divided by h of x. And again, here we have to state our restrictions such that h of x does not equal to 0, because if our denominator equals to 0, our function will be undefined. So this is now the rule for quotient. So to find the derivative here, we take the derivative of the top. So we do g prime of x times the bottom, which is h of x, minus the derivative of the bottom, so h of x times g of x. And then we have to divide all of this by the denominator squared, so by h of x all squared. So this is the quotient rule for finding derivatives. So let's go ahead and do another example. So here, in this example, we have that f of x equals to 2x over x squared plus 1. Okay, so now we'll do this something similar. So we can define that our function on the top over here, that we have our g of x on the top on this numerator, and then h of x as our denominator over there. And so we'll do something similar. Let's find the derivative of g of x. So using power rule again, we get that it equals to 2. And then finding the derivative of h of x, we're going to use a power rule once more. and we get that it is 2x. And now we're going to put this into our formula up here so we can find the full derivative. So as a result, we get that f prime equals to, so g prime, so 2 times h, so 2 times x squared plus 1, and then minus h prime, which is 2x, multiplied by g, which is also 2x here. And then we're going to divide all of this by h squared. So we've got x squared plus 1, and then we're going to square the whole term. So again, this can be further simplified, but for the sake of time, I will leave that as an exercise for all of you to practice your algebra. And the last rule we're going to cover today is chain rule. And chain rule is very important. It lets us find the derivative when we have composite functions. So a composite function means you have a function within a function. So for example, you would have f of g of x. So normally I said you'd have some f of x, where here, instead of just having x, you have an entire function g of x. So you can think of it as an inside function and an outside function. And chain rule is used a lot when we're in machine learning, when we have like neural networks and we're doing back propagation, because we have so many different variables that we have to take the derivative with respect to different ones. So that's why chain rule is very important. So it's good to understand the mathematical foundation of how this works. So essentially what chain rule says is if we're finding the derivative of this, we take the derivative of the outside function, so we do f prime times g of x, and then we multiply this by the derivative of the inside function, which is our g of x. So this here is how you would take the derivative using your chain rule. So let's see an example of how that works. So here we have x squared minus 5x all to the power of 3. So how I want you to think of this is that our outside function here is going to be, I'll just see if I can highlight it for you, is going to be our to the power of 3. So everything I've highlighted, that is kind of considered as our outside function. So we can almost think of that as x to the power of 3 as our outside function. And then the remaining part within would be our inside function. So x squared minus 5x here is now our inside function. So we can see it's kind of like you have to peel back the onion. So you start with your inside and then you work your way out. So following our chain rule over here, let's see if we can find the derivative. So we'll just call this, for this case, f prime. So here we take the derivative of the outside function. So we know we can use power rule because we have an exponent. So we're going to bring down our 3. And like I said, over here, we keep the inside the same. So we keep it as x squared minus 5x. And then following power rule, we have to do 3 minus 1. And then now we have to go ahead and take the derivative of this inside function. So again, following power rule, we'd end up with 2x minus 5. So here we have 3x squared minus 5x to the power of 2 multiplied by 2x minus 5. So again, you had the outside function and inside function, and you were able to kind of work with both pieces to find the overall derivative. So everything we've covered up to this point has been single variable calculus. This means that we've only had one independent variable. And our independent variable so far has just been x. So that means we're putting x as the input into our function, and then our dependent variable y or f of x will vary depending on our input. But what if we were to have more than one independent variable? So that's when we enter the realm of multivariable calculus. So in multivariable calculus, so let's write that out, So in multivariable calculus, you have more than one independent variable. So for example, you could have f of x, y. You could have f of x, y, z, w, and it can go on. In math, it's really neat that you're not limited to the dimensions that we have on Earth. So on Earth, we only have 3 dimensions. We can't really see into a 4th or 5th dimension, but in mathematics, you're not limited by this. You can have 5 dimensions, 100 dimensions, 1,000,000 dimensions, and you're still mathematically able to solve the answer. And what's really neat is that often to solve real world problems, we actually have to work in the 4th, 5th, and 6th dimension mathematically to find a solution for something that works for us. So that's kind of why we're going to start to explore multivariable calculus today. So for the sake of our time and examples today, we're just going to be considering f of xy. So we have a function and we now have 2 independent variables, x and y. So that means that they can both be found in our equation. So we might have something like xy plus y cubed minus 7. So now we can see that we have 2 independent variables that are going to be altering the output of our function. So this is where partial derivatives comes into play. So traditionally, when we were taking derivatives, we were looking at the derivative with respect to x, because that was our only independent variable. But now that we have 2 independent variables, how do we take derivatives? And that's what partial derivatives lets us figure out. So traditionally, I'll just write this another color. Like I said, we could have dy over dx, where y was, or I'll just say d of f of x, essentially, with respect to x. So we were only taking our derivative with respect to x because that's all we had. However, now our f of x, we have f of xy. So then how do we take the derivative? So in partial derivatives, we can dictate which variable we want to differentiate with respect to. So we'll just erase this so we have a bit more space here. So considering our f of xy, let's say that we want to differentiate with respect to x, and we want to differentiate with respect to y. How is that going to look? So if we differentiate with respect to x, we actually use partial derivative notation. So instead of just having a regular d, we now have this symbol instead. So we would do df over dx, and then here we'd have df over dy. So this indicates that we're only taking the derivative with respect to x or with respect to y. But what's interesting in this case is what happens to the remaining variable. So what about y? When we're differentiating with respect to x, we treat y as a constant value. And then likewise, when we're differentiating with respect to y, we're going to be treating x as a constant value. And just like we said before, the derivative of a constant equals to 0. So if it's standalone, beware for that in your equations. So now that you know this, we're going to show an example, and you're going to see how partial derivatives are actually quite easy to calculate, and they're not that much different. We just have to keep in mind this rule over here. Okay, so let's look at our example. So here again, we have f of xy, and this equals to 2xy squared plus x cubed plus y to the power of 6 minus 3x cubed y squared. So initially this might look like there's a lot going on, but I promise as we go through it, it's going to be quite easy to follow. So we're going to start off and we're going to look for the partial derivative of f with respect to x. So again, this means that we're treating y as a constant. And the other thing I want you to note is that each term is separated by either an addition or a subtraction. So that means in this case, we only have to use power rule, and we don't actually have to go ahead and use product rule or quotient rule. So this derivative is actually not going to be too challenging to solve, which is nice to understand how partial derivatives work. So let's start with x. So let's look at our first term over here. So again, we're going to be treating y as a constant. So if y is a constant and 2 is a constant, what's the derivative going to be? Well, if we use power rule, we see that x is to the power of 1. So if nothing's indicated, it's automatically to the power of 1. So following our power rule, I'll just do a little aside over here. So when you have x to the power of 1 using power rule, you get 1 times x to the power of 1 minus 1. So you have 1 times x to the power of 0, and anything to the power of 0 equals to 1. So your final answer is just 1. So that's just a little aside there. So that means that our derivative for the first part is just going to be equal to 2y squared multiplied by 1. And now for this term over here, there's no terms of y, so we're just doing power rule with x as normal. So we've got 3x squared. And then what about this term over here? Y to the power of 6. Well, we're differentiating with respect to x. So since y is treated as a constant, the derivative of a constant is 0. So that value is 0. And then lastly, let's look at our term over here. We've got 3x cubed times y squared. So again, y is being treated as a constant. So we can kind of rewrite this as 3y squared, and we're going to leave that alone. And let's look at our x cubed. Well, following power rule again, we're going to have 3x squared. So we've got our 3y cubed multiplied by 3x squared. So that is the derivative for our last piece over there. Okay, and then we can just simplify this a little bit. So we've got 2y squared plus 3x squared minus 9x squared y squared. And that is the partial derivative with respect to x. So now we're going to go ahead and do the same thing, and we're going to calculate the partial derivative here with respect to y. So that means, again, we're going to be treating now x as a constant. So if we're looking, we'll start with our first term again here. We've got 2xy squared. So following power rule, we keep our constant here, and then we've got 2y by the power rule. The second term, since we're differentiating with respect to y, that means we're going to get a 0 because x is treated as a constant. For our third term over here, we're following the power rule. So we've got 6y to the power of 5. And then lastly over here, again, x is a constant using power rule for y. So we'll just leave our coefficients, and then using power rule for y, we get 2y to the power of 1. So we can simplify this a bit here. We've got 4xy plus 6y to the power of 5, and then minus what we've got. We've got 6x cubed y. And that is the partial derivative with respect to y. So this shows you how you can now take these same concepts of derivatives and all of the fundamental rules that we learned, and then now you can apply them to multivariable calculus. And you can do the same thing for 3 independent variables, 5 independent variables, 100, and you can just keep following these same rules. So it's really neat to see how it's very transferable across multiple dimensions. Okay, so this segues us perfectly into our next topic, which is going to be the topic of gradients. So I'm sure many of you, if you're working in the machine learning space, you've heard of the gradient descent algorithm. So this is used to help minimize your error function when you have neural networks. So again, if you think about a neural network, you're having sometimes billions of parameters. So you can't just take a derivative of one. You have to think about the partial derivative with respect to each of these variables as you go through your algorithm or through your backpropagation. So that's where gradients come into play. So gradients essentially is a collection of partial derivatives. So we'll write that down, of partial derivatives. And a gradient itself is a vector. So the notation for gradient is you can either have this upside down triangle here, and then with f your function, or you can also write it as grad f. So both of these are equivalent notations, and this equals to, oh, sorry, I think here's some chat noises. Everyone's still hearing me all right? Okay, perfect. Okay, so the gradient here is going to be our collection of partial derivatives. So if we follow our earlier example and we're just considering two independent variables, so f of x and y, our gradient of f is going to be df over dx as our first term in the gradient, and then our second term in the gradient is df dy. And again, these are the partial derivatives each with respect to x and with respect to y. So if you were to have more variables, you would just keep this going. So in general, I'll just kind of write a general equation. If we have f of x, and x is, let's just say here x equals to x1, x2, x3, all the way to, let's say, xn, and n is a natural number. So we have all the positive, essentially integers. Then our gradient over here would be our grad f. It would then equal to df over dx1. We'd have df over dx2 all the way to df over dxn. So this general notation will help you understand kind of how far you can stretch it. So essentially, if you have like 100 parameters, 1,000,000 parameters, 1,000,000,000 parameters, you can use this same notation. And just to clarify, this is the gradients for scalar functions. So f is a scalar function in this case, not a vector function, but we're in a multivariable setting, so we have multiple independent variables. So I'll go ahead and show you an example of how we can calculate a gradient. So let's see. So just also real quick, so we said that gradient is a vector. Haven't quite covered what vectors are yet. Here we have these square brackets, and that indicates that it's a vector. And just so you know, okay, so here we're looking to find the gradient of this multivariable function. And here I go. So the x1, x2, x2, and then x2. Okay. So here we're using x1, x2 notation, and we want to find the gradient of this. Okay, so the first thing we have to do for gradients is I always recommend writing out your kind of equation before you start. So here you know that your gradient of f is going to be the partial derivative of f with respect to x1 and the partial derivative of f with respect to x2. So that means we just have to find df over dx1, and we also need to find df over dx2. So it's always good to kind of map out what you're looking for, and I find that really helps limit mistakes. So now we should all be pros at solving partial derivatives. So we're going to just kind of use the same strategy that we use in our previous problem. So if we're looking for the derivative with respect to x1, we're treating x2 as a constant. So here we're going to end up with 20 x1 to the power of 4 x2. And then there's no x1s in our second term, so it is 0. And then our third term over here is going to be 7x2. And then for the partial derivative with respect to x2, we are going to end up with 4x1 to the power of 5 minus 4x2 plus 7x1, all using the power rule. So now what we have to do is very simply to find our gradient, we just have to put these two terms into our gradient vector. So therefore, our final answer here is that the gradient of f equals to, what do we have here? We've got 20x1 to the power of 4x2 minus 7x2 as our first term. And then our second term within the vector is 4x1 to the power of 5 minus 4x2 plus 7x1. So there we go. And now you've already learned how to find a gradient in a multivariable setting. So that's a really important skill to have. And again, like I said, it has so many applications in machine learning and neural networks and really understanding the gradient descent algorithm. So make sure that you remember this one. Okay, so we're going to segue a little bit now into vectors. So I did introduce slightly what a vector was when we were looking at gradients, but we're going to dive a little bit more into this. The reason why, well, there's so many reasons why vectors are important, but if you think about large language models and the embedding space, all the embeddings from your natural language as they go into these like vectors of numbers, these are all vectors, these embeddings. So when you type into a machine, it encodes it into a vector. And then these so many, I guess, mathematical operations are happening to these vectors behind the scenes before you then get your output in natural language. So vectors are really the behind the scenes of most machine learning algorithms, and especially very prevalent within large language models. So we're going to learn a couple really important, I guess, operations with vectors today, just so you get an understanding of like how they work. So the first thing we're going to look at, just to have a little bit of an introduction, is Cartesian vectors. Cartesian vectors. So for Cartesian vectors, we're just going to start in the two-dimensional plane. That way we can draw it out and we can all see what's going on. So for Cartesian vectors, it's typically you have your xy plane. So you have your xy coordinates, and then imagine that you choose some dot on your xy plane. And we'll say this dot exists at 5 and it exists at 4. So we have this point over here, 5, 4, and that is our ordered pair. So whenever we have ordered pairs, we always start with the x coordinate first, and then we have the y coordinate. And then so here, this is simply a point, and well, how can we create that point into a vector? So we're going to start at the origin, which is 0, 0, and then what we're going to do is we're going to draw an arrow from the origin all the way to our point over here. So now this has turned into vector 5, 4. So this is now a Cartesian vector. Like I said before, vectors have to have a direction as well as a magnitude. So this arrow here indicates the direction of the vector, and then we have our 0.54, so we know the magnitude, or also known as the size of the vector. So when you draw vectors, for Cartesian vectors, you use square brackets, and that indicates that you have a vector, whereas round brackets here indicate that you have a point, which is generally not a vector. Okay, so for vectors, you add them from tip to tail. So if we have multiple vectors, these arrows, we'll just say we've got arrows here, and each arrow represents a vector. So we add them from tip to tail. So we call this back end here the tail, and then we call this the tip or the head. Both are interchangeable. So if you have multiple vectors, you add them, again, tip to tail, and then you can just go along. So it's really neat that in vectors, if you actually draw everything to scale, you can do all your operations based on the drawing of arrows, which is really cool. Or if you don't want to do it to scale, that's when you can start adding your coordinates. So we can say our first vector is, I don't know, we can say, let's say 5, 0, and then we have our next vector, maybe it's 4, 1, and so on. So we can add them that way, which is really cool. So that's just a quick background on just Cartesian vectors, so you have some context. The other way how you can write this, you might see an alternate notation that if you have some vector x, y, you can also write it with respect to the unit vectors. So it would look like ix plus jy. So then our vector here, 5, 4, would be 4i plus, got 5i plus 4j. And this is equivalent to vector 5, 4. So these are two-dimensional Cartesian vectors. So this means that we've gone 5 units in the x direction, and we've gone 4 units in the y direction. So now that you know a little bit about Cartesian vectors, I told you that they represent both direction and magnitude. And I want to discuss a few different ways how we can actually calculate the distance or the magnitude of these vectors. So there's two main ways, there's multiple ways, but the two main ways that most people will do this is either with Euclidean distance or with cosine distance. And cosine distance is also known as cosine similarity. So both of these metrics, again, are very crucial in the large language model space. I've done lots of research projects with language embeddings, stylistic embeddings, and we use both these Euclidean and cosine distance metrics to determine the similarity between different speaker styles. So if we have two embeddings that are very close together, we would consider that these two speakers have a more similar style of speaking. So this shows you how you can take these mathematical, almost abstract concepts and apply it to real life and real world problems within language models. So we got Euclidean distance and we've got cosine distance. So Euclidean distance is more, if you think of the distance between your and your friend's house, it's 1 kilometer away, that would be a Euclidean distance, where a cosine distance deals more with the angle. So what is like that angle between two vectors, for example? So we're going to break this down, and I'm going to show you how to calculate the Euclidean magnitude or the 2 norm, and I'm also going to show you how to find the dot product. Okay, so with Euclidean distance today, I'm going to show you 2 norm. And for cosine distance, as an application, I'm going to show you dot product. Okay, so we're going to start with number 1. So we're going to start with the 2 norm. So in vectors, there's many different ways how you can calculate distance, various different types of what we call norms. So the 2 norm is also known as Euclidean magnitude. So I know there can be lots of jargon sometimes in this, but this is why I'm just showing you the different types of words or notation that we can have, just so you can recognize them as the same thing. So for this, say we have some vector, let's say we've got x and y over here, and we want to now find the magnitude. So say this is going to be called vector A. So vectors also, we denote it by having this little hat on top. So if we now want to find a magnitude of this, we put these absolute value signs on either side of A, and we calculate this by taking the first term squared plus the second term squared. And if you know anything about trigonometry, this essentially is Pythagorean's theorem. So we are finding that almost hypotenuse, you can think, between the 2 points, because you can think we have our x component here, and then we've got our y component, and then what is the actual magnitude? Essentially, we are looking at this resultant vector over here, this hypotenuse, and that's going to give us our magnitude A. So again, neat how trigonometry relates with all of this. So that is the 2 norm. So if we do a very quick example, let's say A equals to 2, 3, then the magnitude of A here would equal to the square root of 2 squared plus 3 squared. So we've got the root of 4 plus 9. So as a result, we've got a root of 13 right over there. And that would be the magnitude. This is just a size. Okay, so now we're going to move on to the second type. So here we're looking at dot product. So earlier I mentioned cosine similarity. So essentially, cosine similarity or cosine distance is the normalized version of dot product. So I'm just going to show you dot product first, and then we can go into that application. So for dot product, I want us to consider that we have 2 vectors. Say we have vector u, and we have vector v. So whenever you take the dot product, your 2 vectors have to be lined up tail to tail. So when I said when we add vectors, we align them tip to tail. However, when we use dot product, they have to be aligned tail to tail. And then we need it in this way because we're interested in the angle or theta between these 2 vectors that are lined up. So again, when you use dot product, make sure that your vectors are lined up in this format. So there's 2 different definitions that we can have for dot product. So I'll start by showing you the first. So in this case, we're looking for the dot product of u dot v. And this is how you show dot product, literally a dot between them. So don't get confused with multiplication because this has a different meaning. It's specifically dot product for vectors. So to find the dot product, you take the magnitude of u multiplied by the magnitude of v, and then you multiply that by the cos theta. So this is why I showed you the magnitude formula earlier, because it's embedded within this formula. Okay, so the second notation is, say, I guess we just need a bit more information here. So say we have our vector u equals to u1, u2, and say our vector v here equals to v1, v2. So if we do our second definition for dot product, we have that u dot v equals to, what do we've got here? u1 v1 plus u2 v2. Okay, so we just can take the components directly from our Cartesian vectors over there. And the most important thing that I'm going to tell you here is that the result of dot product is a scalar value. So scalar value means that it is not a vector. And since it's not a vector, it means it only has magnitude, but no direction. So dot product, like I said, can then be used for cosine similarity. So then if you divide the dot product by the lengths, if you normalize it, then you end up with cosine distance. So dot product is very important there. And the other thing is dot product is often used to determine whether two vectors are orthogonal. So orthogonal means perpendicular. So if two vectors are perpendicular, that means the angle between them, theta, equals to 90 degrees. And I want us to think about the cosine function. When cos is 90 degrees, this would be right over here, then the function equals to 0. So cos of 90 degrees equals to 0. So that means that if your dot product equals to 0, that means that if you don't have 0 vectors, then your two vectors are orthogonal or perpendicular. And that's huge in mathematics. We're often trying to determine whether vectors are orthogonal, and then you can quickly use the dot product to check, okay, is it 0? Then most likely then your two vectors will be orthogonal, which is a great kind of bonus property that it has. Okay, so now that we've done dot product, we're going to switch gears a little bit because I want us to cover our last topic, which is eigenvalues and eigenvectors. So, yep.
Just a reminder that we have 7 minutes left for this session.
7 minutes,
and
yes.
We have another session right after this.
Okay, perfect. Yeah, we'll make sure to finish on time. Thank you. So for eigenvalues and eigenvectors, the biggest application for machine learning is principal component analysis. So principal component analysis then helps us with dimensionality reduction. So that is huge because sometimes when you have massive problems with so much data, you can't possibly process it all. So you use your eigenvalues in principal component analysis to reduce the dimensions of your problem. So I'm going to quickly show you how to calculate the eigenvalues of a 2x2 matrix, because then this can be further expanded into higher dimensions. So you can think of eigenvalues as the roots of matrices. And essentially, eigenvalues tell you how much a linear transformation scales along an eigenvector. Is it stretching it? Is it compressing it? Is it rotating it? So this value, this one scalar value can tell you all about a linear transformation. So say we have some A, which is a matrix A. We find the eigenvalues by taking the determinant of matrix A minus lambda I and set that equal to 0. So again, we have our matrix A. Lambda is going to be our eigenvalues. I'm just going to write it like this. And I is our identity matrix. So we're just going to go through a very quick example, and I'm going to show you how to find this. So consider, let's have our matrix A equals to 0, 1, -2, -3. So now we're going to set it up. We're going to take the determinant of a minus lambda I. So det of a minus lambda I, this equals to, so we'll only affect the values along the diagonal. So you've got 0 minus lambda, 1, -2, and then we've got -3 minus lambda. And the determinant of a matrix, if you have A, B, C, D, the determinant equals to, what do we have here? AD minus BC. And that's what we're going to do right over here. So we've got negative lambda times -3 minus lambda minus -2 times 1. And if we expand this, we get lambda squared plus 3 lambda plus 2 equals to 0. We're going to factor this. So we get lambda plus 1, lambda plus 2 equals to 0. And as a result, lambda 1 equals to -1 and lambda 2 equals to -2. So we've found the two eigenvalues of our 2x2 matrix. And I'm just going to show you the definition to find eigenvectors. So you would take your matrix A, and then V1 equals to lambda 1 V1. And in this case, you see that the V1 is your eigenvector, and then lambda 1 is your eigenvalue number 1. So you would do the same process for both of them, and that allows you to find your eigenvectors. And essentially, the most important thing here to remember is that your largest eigenvalue corresponds to the eigenvector that incorporates the most variation in the data. So that over there would be your first principal component. And then you can use that for your PCA and dimensionality reduction. And with that, I'll end the session today. I know that was a lot of information. I hope all of you learned a bunch. And yeah, please feel free to reach out to me if you have like any other questions. And what I'll do now as well is I also started a math YouTube channel where I cover most of these topics as well in greater detail. So if you want to learn any more about any of these topics, be sure to check that out. And I'd be more than happy to kind of answer any questions you have over Discord and anywhere else. So yeah, it was really nice seeing all of you today, and hope you enjoy.
Thank you. Thanks, Katrina. I think, well, if you can, put the link to your YouTube in the chat now so that people can follow up. We've got ongoing math sessions with Katrina and Neil in our Discord, so we'll hope to see you at some of those in the future. Any other housekeeping before we sign off? We've got another call directly after this with Niels Raymer, which will be really great. Unfortunately, just logistically, we'll need everyone to sign off this call, and then we'll rejoin it at the same link. Ahmed, what else do we say to close out the session?
Thank you so much, Katrina, and thank you so much, everyone, for joining. Please, we were a little behind on the time, so feel free to ask any question on the Discord or reach out to Katrina and just rejoin this link. We will end the call for a while. Thank you so much, everyone.